Hello everyone, my name is Bernard de Breen and it's my pleasure to be here with Dr. Carlos Collet, one of my co-workers here in the Department of Interventional Cardiology at the Cardiovascular Center Aalst. What we are going to do today is actually to illustrate how we perform continuous thermodilution. Not bolus thermodilution, as we are used to do for measuring IMR, the index of microvascular resistance, but continuous thermodilution, which enables us to measure absolute flow and absolute microvascular resistance. It means absolute flow in milliliter per minute and absolute microvascular resistance expressed in Wood's unit. To perform this continuous thermodilution, we need actually three pieces of equipment. A pressure/temperature guide wire as produced by Abbott. Second, we need a dedicated infusion catheter, which is called a RAYFLOW catheter produced by HEXACATH, which has to be connected to a pump filled with saline at room temperature. And we need a software called Coroventis to calculate all these measurements online. On the Coroventis monitor, which is displayed on the boom, we see from top to bottom the aortic pressure tracing PA, as recorded by the guiding, the distal coronary pressure PD, recorded by the pressure wire X, and in blue, the temperature of the blood in the distal part of the coronary artery. How to do in practice? Well, in this patient we see the coronary arteries are normal or near normal. The pressure wire is equalized in the proximal part of the artery, and then the sensor is positioned in the distal part of the vessel. The monorail infusion catheter is then mounted on the wire, where you can see very well the 4 jets of saline coming out of the RAYFLOW catheter. While flushing, the catheter is introduced in the guiding. The rationale of these 4 lateral holes is to enable a complete and instantaneous mixing of saline with blood. The RAYFLOW catheter is advanced into the proximal part of the artery to be assessed, while the sensor is located in the distal part of the vessel. Important to notice is that the flow is actually measured in the proximal part of the vessel where the saline is infused. Now we are all set with the RAYFLOW catheter in the proximal part of the LAD and the sensor in the distal part. On the Coroventis we select the right program, namely absolute flow. We zero the temperature and we start the recording while starting the infusion at 10 ml per minute. We will soon observe a decline in distal temperature, which in this case will stabilize around 0.40 degrees Celsius. Please note that there is no change in PDPA ratio, which confirms that we remain under resting conditions. After 2 minutes, the pump will automatically switch to an infusion rate of 20 ml per minute, thus inducing maximal hyperemia. The distal temperature will soon decline further. Also, the PDPA ratio decreases and stabilizes around 0.81, indicating that now we have achieved fully hyperemia. When steady state is reached, the sensor is pulled back into the infusion catheter. A sudden drop in temperature is noticed, in the present case to -6.8 degrees Celsius, a figure which corresponds to the temperature of the saline when it enters the coronary artery. And then again, the infusion rate will go back to 10 ml per minute, thus allowing to measure the temperature of saline when it enters the coronary artery at this infusion rate of 10 ml per minute. Now we can stop the pump as well as the recording. It has taken a bit more than 4 minutes, and there has been minimal interaction with the operator. As soon as we stop the recording, the software will provide us not only with fractional flow reserve values, but also with absolute values of flow in milliliter per minute and of microvascular resistance in Wood units, both at rest and during hyperemia. And finally, FFR, CFR and microvascular resistance reserve, or MRR, are instantaneously displayed